we are going to start to look at the code and how we are basically writing this assembly language code. So as you've seen before, your program is basically a plain text file, and you are basically typing your code in there. And usually the suffix of that or the extension of that file is .s. So I'm going to show you how we can actually run that. But before that, the code is actually divided into two general sections. So we have a data section and a code section. So data, which is marked by the directive .data, so that's kind of like a keyboard that you have, and you start this section with this, is basically you all the things that you are supposed to have in your memory, you're gonna place in your data section. So that could be like if you have some assigning some variables, if you're assigning some let's say arrays. So all the space that you need in your memory, you have to basically assign it at the beginning in the data section. And then you have your code section, and that is marked with the directive of .text, which basically is going to be your instructions. So of course, your program going to initialize this first, and then it's going to go through this code section and run each instruction one line after another. So here we see a basic template, and these the hashtag sign is basically the comment symbol. So these lines are ignored by your assembler, so it's not going to be executed on the CPU. And you have them also in the line, like after some instruction, and then you can have the comment also. So this is what I was talking about. You have the .data and .text, and those are directives that's showing basically anything after this to this section is the data section, and then anything after this is the text section. So your code is actually going here. Here you have all your variables. And then you have this thing that you see, here's a label. So labels are basically markers in your code that we're gonna see more, but basically you can think of it as your, like here that you have the main, you have in Java or C, you have your main function that is basically a starting of the code. But it is not a reserved keyword, so you can have any other label here. So the typical format is that you have an operation and you have three operands. So we're gonna see like different formats, but this is the most that you're gonna use and the simplest one. So operation, of course, is like something like add or subtraction. And these three are basically three variables. Okay, there are three registers. So what we have here, for example, if you are doing this add and then S0, S1, S2, it actually, so this is like the order here is important. So it actually means that you're adding this two number and you're storing the result in S0. And if you're doing a sub instruction, it's basically it's S1 minus S2, and then the result gonna be stored in S3. So sometimes you can have constants also. So there are a specific instruction that like this I is indicating that it is a constant or immediate, and you can have your third argument here as a constant. So we're going to see later how actually the assembler is taking care of this and converting it to series of smaller instructions. But basically this is the basic instruction that we are looking at here. And we don't have sub I because basically you are using add I and you have a negative sign with that. So MIPS is a load store architecture. What does it mean? It means that our instructions that we have are only working with registers and constant. So as you saw here, we have like registers and constant here. We cannot directly deal with memory. So we cannot like add two things in the memory directly. So what we do first, we are basically loading it to some register, so one of these, and then do some instructions on it, and then we save it back to the memory. So that's what we mean by load store architecture. And yeah, so the way that the compiler does, so let's say if you are doing in higher level language, let's say you are programming in C, the way the compiler actually um, assign these are, it's trying to be efficient. So it's gonna be like using using some of these register that gonna be um, using your code, and it's gonna basically trying to, because you have limited number of this, so it's trying to save this loading from the memory and back, and it's basically trying to minimize that. And it's gonna be faster in that way because your registers are very fast compared to your memory, but the problem is that you don't have enough registers. So you have to basically have some of them in your memory and then load them back, do some instructions, and then basically having this um, trip between the memory and your registers all the time. So here is the first thing that we're gonna see. We have a very basic um, arithmetic command. So we have some like addition and subtractions, and we're gonna see how actually we can turn this into assembly code. So when you run this code in, let's say, C++, you're initializing some variables here. So the compiler actually decides how it's gonna assign this variable to your registers. So let's say this is what it designed. So this is our assumption that the compiler has decided on this. So it put, for example, the value for the V to your S0, and it put the value in W to your S1, and so on. And this is basically your main, and basically the main instruction that you're having in your code. So let's see how we can translate that. So if we go back, um, so this data section we are not using now because we are using everything and storing everything basically on the registers. So let's look at the first line. Here we have add I S0 0 0. So what's happening here? We are adding S0 with a constant 0 and storing that into S0. So basically this is going to be always 0, and we are saving that to S0. So S0 was V, and V is initialized to 0. So that's how basically we are doing these initializations. W is 1. So we have the add I S1, S0, and 1. So $0. So this is 0, and plus 1 is going to be 1, and we are storing that into S1. So all of these instructions, the 5 here that you see, they have this $0, which is a constant 0, and here we have the initial number that are there. So basically we are doing this 0 through 4, and we are assigning to the variables, but we are using the S, 0 to 4. And then the next step is that we are adding, we are going through these instructions. So the first one is actually assignment, it's not an add. So we can use the same tactic that we used here. So we could do an add, and if you remember, there was the add, we had an add I and an add. So this one, the difference is that they are all registers here. I mean, we could do also put S0 here and have a constant 0 here. That would work also. But we chose to do this one. So we have the $0, so that's 0, plus S4, which was Z, and we are storing that into W. So basically this means W is equal to Z. And then if we have the next one that we are adding W and X, we simply put the two registers that are containing this value. So W is 1 here, and X is S2. So we have S1 and S2, and the content of that gonna be stored in S0, which is V. And then the same thing for the subtraction, and you just have to remember that is this one minus this one. So it's S1 minus S2 here. And if you look at them, it's gonna be W minus X, and the content gonna be here. And here we have the last one is Z minus 1. So we can do an add I with a constant minus 1. And this last thing here, we're gonna talk about it, and we're gonna see it later also. but basically this is ending the program. So this is a special signal, the number 10, that we are putting it in v0, and then when you do a system call, basically it's going to look at content of the v0 and see what signal you put there, and based on that it's going to do some action. So in this point 10 means to exit the program. So that's how we basically do a basic translation, line by line. First we assign the initial values and we have your registers, and then line by line we can translate that.